Those of you who don't know me may have figured out by now that I have some roots in the Naval Nuclear Propulsion Program. My first boss was Rickover, so the first 10 years of my career was in those things having to do with naval reactors. So this is, I learned nuclear energy in the context of the Naval Nuclear Propulsion Program. And as I mentioned earlier, and I want to go back to context, I remind you where we are. We are in this Cold War. Our priorities are Cold War priorities. The fact that there are folks, as Roger outlined in the political, social environment, we're trying to move towards nuclear power, electric power generation, and we're looking at a bunch of different technologies, as Finis elaborated, some with some success, and other cases not so much success. All that's going on, but the real focus is now in the how do we fulfill that nuclear triad I showed you? How do we, in the Naval Nuclear Propulsion Program, how do we do our part of that job? How do we fulfill what needs to be done? So context, I bring you back, is we're in nuclear weapons development and nuclear energy for propulsion in submarine and surface ships. And peaceful uses of nuclear energy take a back seat. No matter what Eisenhower may have been trying to do at the time, the realities of that environment and the priority was how do we fulfill our obligations and from a Cold War standpoint and do our part in that nuclear triad. In the midst of this, we've touched on this, that nuclear energy technology was born secret. That's the terminology people like to use, okay? It's all classified, not secret, but it's all classified. How do we deal with that? The things are in classified versions. We got to bring in the industry because it's a government-directed program, but industry has to implement it, execute it. And how do we bring that industry to bear, and how do we deal with classified information? And because we have to have all these people involved in that discussion. And we have this misalignment, which I won't go through again. But let me remind you this. But here it is, the beginning. If we come out of World War II, the Navy's not sure what its post-war and future fleet should be. Just not sure. We just succeeded in a war. We had a particular fleet characteristic. We're trying to figure out what is our future. Not clear. Atomic Energy Commission now has exclusive authority over nuclear energy research and development, but it's uncertain where it wants to put its priorities. As Roger laid out for you, weapons priorities, propulsion priorities for this, power reactors. Where are the priorities? And all this tug of war within government, the National Security Council, the Atomic Energy Commission, the Congress through the Joint Committee on Atomic Energy. And if Roger didn't underline that hard enough for you, the Joint Committee on Atomic Energy was a tremendously powerful capability within our government that we haven't achieved again. Okay, it's something that occasionally people say, why don't we do something like that again so we can get something done? There was an emerging perspective that nuclear energy could be transformative in the future of submarine warfare. This is, you said, well, we had submarines, okay, through World War II and earlier. The answer is no. They were surface ships that sunk periodically, okay? And they weren't truly submersibles. And so the issue is, can we get to a true submersible? Difficult to detect, practically unlimited cruising range, and its duration on mission. A machine that was built to be under the water, okay, not a machine that was built to be on top of the water and occasionally go down. And hopefully you have an even number of transitions between the two, okay? Now, some important, and I won't go through all those of you who are industry buffs and want to go through these, history buffs and want to go through some of the development of this area, there are books that go through it. But the issue is there were some important personalities. Rickover's been mentioned. He was driving. He had a very singular objective. His objective had to do with how do we get reactor in a submarine, and later, how do we get a reactor in a surface ship and be successful? And not get distracted by the science. Now understand how I'm going to say this. If the national labs had the lead, we'd have great science, but probably no submarines, okay? Because the issue is the national lab personality is to understand, to learn, research, development, understand. Rickover in the nuclear Navy's perspective was, how do we go get something engineered, built, now done? Okay, and the science we needed to make that happen was only the science necessary to make the engineering successful. Okay? There's a difference in that approach, which you'll see through the histories of this program. Very important gentleman in this is Admiral Chester Nimitz, the Chief of Naval Operations after the war. The USS Nimitz aircraft carrier is named after him. And he gave impetus to this whole thing, and he saw that future with Rickover and others that had that vision. So it turns out, and it was Captain Rickover at the time, certain A&C commissioners, senior naval officers, National Security Council, and Congressional Joint Committee finally found their, and I use the word bludgeoned here because that's almost what it took, bludgeoned their way through the bureaucratic maze of the U.S. government to finally achieve agreement to proceed with reactor development for submarine application. It took direction out of all these organizations to get us headed in a one direction. But now then the next question is, who's in charge? Atomic Energy Commission owns nuclear energy. Navy owns the ships. Congress owns the money. The national labs are fighting for a controlling technology position. As I said, oriented towards the science of nuclear energy. And it painfully, and I'll use that word here on the slide, it evolves into Rickover taking increasing authority into two organizations, and this is fundamental to the success of this program. He had authority both in the Atomic Energy Commission and in the Navy, with direct support of the Joint Committee on Atomic Energy. Now let me underline that because it's very important to the success of that program. When I worked for him, as an example, I had authority in the Atomic Energy Commission, or DOE later, and in the Navy. You've heard the old stories that Rickover could write himself letters, okay? One agency to the other to get something done. Now, it's important that, and I use Rickover here, but it's really Rickover and the people he surrounded himself with who were driving toward this success. And the Joint Committee, which was Rickover's power base, not the Navy, the Joint Committee on Atomic Energy. That's the power base for the Naval Nuclear Propulsion Program. Argonne and Oak Ridge take the initial technology development roles, very important roles in that early work to set the course on where we were going to go. And it evolved, and I won't take you through the evolution, but it evolved then into two dedicated atomic energy, or AEC labs for the naval program, the Bettis Lab and the Knowles Atomic Power Laboratory, which I understand a couple of folks here have worked at. At that time, Bettis was operated by Westinghouse for the government, and the Knowles Atomic Power Laboratory was operated by GE. They worked hand in hand with the Electric Boat Shipyard, Groton, Connecticut, today General Dynamics, to design and build the first nuclear submarine. This structure, a two-hatted government capability in the AEC and the Navy, dedicated laboratories, Westinghouse and GE, very strong companies that could lead this, all came together to help fulfill the vision that the Navy needed to get a true submersible in place. But part of the question was, what nuclear energy technology? And let me talk to you about submarines for just a second. I won't run this into a submarine discussion very deeply, but just talk about it. Here's a simplified spec for a nuclear submarine. Somehow I got to find the minimum weight and volume for the propulsion plant. I I'd like it to be about the size of a pinhead, okay, if I could get away with it. Because the ship has its purpose is to move weapons around, right? That's its job. And I want it to look like a fish, the thing called an albacore hull, you that may have that background. And all this imposition of putting a propulsion plant in there to achieve what we were trying to achieve, it was an imposition, literally an imposition. It required us to go away from the shape of a fish. Now, this is no longer the fleet boats of World War II. This is now a true submersible, okay? I had to get to the maximum achievable speed. There's all types of mission needs to do that. And I won't go through the specifics here. I had to have unlimited submerged duration. So I had to have my own ability of atmosphere, closed device, submerged, okay? I'd have platform stability if it's a ballistic missile platform, okay? I can't be wandering around when I'm trying to fire a ballistic missile targeted at our favorite enemy, okay? I have to have platform stability. And I have to have a robust propulsion plant designed. And let me dwell on that for just a minute, okay? This isn't a static device. This is a ship, a boat, if you will, a submarine. And it has to be highly maneuverable. It's a battle machine. It has to be unaffected by extreme ship motions. You know, the little picture at the right there gives you an idea of all the motions you go through. This is a nuclear plant that I have to be able to move all kinds of directions whenever I want it to, okay? Or whenever the sea decides that's what it's going to do with it, okay? And there's fixed rotationals and there's translational rotationals, etc. And it has to be battle hardened. And battle hardened means that it has to handle huge shock loads, the loads that you're used to considering in seismic design of power plants are minuscule compared to the requirements for a battle-hardened submersible submarine with a nuclear reactor in it. And it has to be simple to operate. The term we used at the time was sailor-proof. Okay, that was kind of derogatory, but that was the thought. Okay, how do we build something that's simple enough that the operators, and this is where George's career started, okay? How do we make it simple enough the operators understand what this thing is, can operate it well, okay? And they can also maintain it. Because you can't just always drive back to the garage and get the thing fixed, okay? You're deployed forward. You have to be able to maintain major parts of this plant. And I'll go one more thing that I haven't put in here on the slide, but I'll mention to you, is the submarines have the ability, not only our nuclear submarines, but a large amount of the military force, to go to a condition, what did you call it in your boat, where you flip the switch and you're in battle short? Okay, battle short, which basically says I remove the protective features on the reactor. So the reactor has to be designed in a manner that's very robust to let it continue its mission without challenging the safety of the reactor, but with no protective circuitry in place. Because the last thing I want to do is have this reactor scram in the midst of a battle situation. It's just not the right thing to do, okay?
Phil? Yeah, we also had it that had a fast scram recovery ability too, because...
Go ahead and explain that.
Even if you did trip, you wanted to recover that propulsion plant very, very quickly, and so you would be able to withdraw the rods extremely fast, place the reactor on a very high startup rate, and carry it forward. So, yeah, it was designed as a weapons device, without a doubt.
Right. Now, and if I take that, we used to call it catching the rods on the first bounce, you know? Control rods hit the bottom, you grab, off you go, okay? Which is not at all the commercial reactor thought process. And the propulsion plant had to be, when I said here, highly maneuverable. Think of two orders of magnitude faster than the commercial reactor maneuvers today. Okay? Those were the requirements that this machine had that was now the foundation for what we will evolve into as we go through these storylines, do a commercial reactor. So its needs were a lot different. The design was a lot different. The philosophy of its design is different than a commercial reactor's needs. So as we will make the transition, and I'll get to that in a few minutes, as we make the transition towards a commercial world, we had to make some decisions as we go towards a commercial world, some of which were good, some of which weren't so good, because we were going off a machine that was designed for a different purpose, not to generate power in a static environment on the land, but to do the types of things that we just talked about here. So what technology? So we evaluated several, and these were brought to the fore by Argonne and Oak Ridge in terms of the most promising technologies at the time that we needed to find our way through and decide what the right choice was. Pressurized water thermal reactor, translate that to what became the S1W prototype for the Nautilus prototype. But that's the closest to what a PWR is today in the commercial world. A helium-cooled epithermal reactor, a sodium-cooled intermediate reactor, not quite fast spectrum, intermediate spectrum reactor. We also looked at an organic-cooled concept, but Finnis gave you a good idea why that one didn't work out so well. Now, based on these initial studies, we ended up with two primary approaches. The submarine thermal reactor, so-called, that's just a name, the PWR, which was what the S1W prototype that was in the Idaho desert, and the S2W, which was in the Nautilus, the first nuclear submarine. And then the submarine intermediate reactor, a sodium-cooled reactor, in the S1G prototype, which was at West Milton, New York. Many of you have seen the big containment ball in some pictures at West Milton. That's where that plant was built. And that containment was for that purpose originally. And then in this submarine called the Seawolf, where we ran the sodium-cooled reactor, and both now for PWRs and sodium-cooled reactors, to gain the experience of what it meant. And what was the right choice? As it turns out, and this wasn't, it wasn't like it was a surprise. We had some insight, but it was a surprise in the sense we didn't quite recognize the extent of differences. The S1W prototype and the Nautilus were exceptionally successful in the reference nuclear energy technology approach for all subsequent U.S. submarine propulsion plants. It has turned out to be the right choice for the naval application. There's no question about it. The sodium-cooled prototype and the Seawolf had a lot of material problems. I won't read this to you. You can read it off the slide. A lot of problems. Now, if we had failed to be successful with the water reactor, we would have solved the problems of the sodium-cooled reactor, and it could have become the reference design for our submarine fleet. And in fact, our friends, the Soviets, who were working madly at the time to do the same thing we're trying to do, okay, they were looking at alternatives, and they came up with some that were different conclusions than we came to. And they had a lot of problems with those, okay? Lead-cooled, sodium-cooled, okay? They made some decisions that were different. They came up with a different set of criteria, a different set of answers. Fortunately, ours turned out to be better than their answers. That's, there's a lot of history in that discussion. Now let's talk about shipping port. This has been brought up a couple times by Roger and by Finnis. Shipping port to the naval program and to Rickover was a distraction, but it turned it into an advantage. And it's interesting that within 1 month of the S1W prototype beginning full power operation in June of 1954, 1 month, we just started this first pressurized water thermal reactor up. In 1 month, we make a decision to build shipping port. We didn't know a damn thing about the experience in this reactor, but the government's pushing now to go commercialize nuclear energy. And so these power reactor activities that Roger walked you through of these various programs, what are they, 3 rounds?
4, counting that first selection of 5.
Okay, 4 rounds then. All that's going on. Meanwhile, we said, all right, we're going to do all this stuff, and we can decide who's going to pay for it and all that, but we're going to go build shipping port. what turned out to be called shipping port. And at the end of the day, Naval Reactors is going to drive it. And that was not an easy decision in government for a number of reasons, but I won't drag you through it. But it was not an easy decision because there were a lot of people in government who just hated Rickover. So you had the personalities work your way into this thing, okay? And they wanted to keep this out of his hands because they knew what he was going to do, which he did. He's going to make this look as much like he could, like something that was usable as a ship propulsion plant. He was going to use the shipping port plant not only to demonstrate commercial, which was his task, but to use what he developed within that technology for larger plants. Shipping port's a much bigger reactor than you find in the submarines. So the so-called power reactor project, the demonstration power reactor project, designed and built in a power ship between the Atomic Energy Commission and the Duquesne Light. Basically, the AEC, under Rickover's lead for this part of it, for the reactor, Duquesne Light for the balance of plant. They basically said, we'll supply the balance of plant, government will provide the reactor. Reactor plant designed by Westinghouse, through Bettis, Stone & Webster Engineering Corporation, which doesn't exist anymore, but I think enough of you recognize that term, where they came from. They were most recently subsumed under different names by Westinghouse, okay? They're part of the Westinghouse organization today. And the steam plant design by Burns & Rowe. Is Burns & Rowe still around? I've lost track. I don't think so. Now, the shipping port reactor plant was extrapolated from preliminary work for an aircraft carrier propulsion plant. And with basically the naval features removed and declassified to facilitate technology transfer to the private sector. I'm now looking at what Rickover's charge was. This was his charge. Build something, commercial prototype, or demonstration rather, get the naval features out of it. We didn't fully achieve that. We kept a lot of them in intentionally. And declassify the technology in such a way as it doesn't cause a problem with the Navy's needs, but at the same time allowed for the technology transfer to the private sector. And there are thousands and thousands of technical reports that were developed out of that activity. In 3.5 years, we went from the concept of what you and I are talking about here to an operating power reactor at shipping port. An important consequence is that technology then becomes a choice for the majority of commercial reactors globally as a result of this demonstration here. And I won't go at this point. I'll talk about it in a few minutes when I go through the next presentation on commercial reactors, commercialization of reactors. But because we had spent so much effort in developing this particular technology for the purposes that are of interest to the Navy, that set the framework and the groundwork for commercialization and propelled that. It's not because we had gone through how many reactors finished? 62? 62 different technologies and made a choice. We had picked one that worked for this purpose, and then it got propelled through other purposes like politics and national strategies and that kind of thing into a global environment. We'll talk through that in a few minutes. So within the next decade, this is now, we get scared. This is the late 50s, 58, that time frame. When was Sputnik, 57? 57. USSR, Soviet Union, successes in weapons development, nuclear submarines, intercontinental ballistic missiles, Sputnik, the first satellite, for those of you who don't have that in your memory, and propelled the U.S. military-industrial complex into a massive shipbuilding program using nuclear propulsion. There are multiple submarine designs using PWR technology developed to meet the increasing demand. And you can see, I just listed there without explaining them, attack submarines, ballistic missile submarines, hunter-killer submarines, cruise missile submarines, radar pickets. The ones we ended up over the longer term actually focusing on were the attack and ballistic missile submarines, with a few of the cruise missile submarines thrown in, okay? But we looked at propulsion plant design, evolution. We changed the design as we were going forward, but again, it's focused on how do we move this weapons delivery platform around. We also, in building out a shipping port and a lot of other work, went and put propulsion plants on aircraft carriers, frigates, guided missile ships, and this type of thing. Now, this aggressive shipbuilding program extended into the 1980s, and important offshoot of that to the commercial world is it developed the industrial capability that was then used by the commercial world. We built the industrial capability for the Navy's purposes, but it basically established the industrial capability for the commercial nuclear world. We used to have, just as a story, we used to have welding school at outside of Mystic, Connecticut, and we had a hard time getting enough welders through that could build submarines, and at the same time, the commercial world was reaching in and stealing them, and they made a whole lot more money. Okay, so it was a race to get the resources and the people. Now, there's an important part of this which has to do with the engineering approach taken in the Naval Nuclear Program. The project methodology focused on engineering with only that science necessary to complete the design. Very important aspect if you want to get something done in a hurry. Okay? And we did. We didn't have a choice. You know, we had to get Nautilus out it took us 4 to 5 years to get Nautilus out, 6 to 8 years to get, depending on what year you start with, to get the Enterprise, the first aircraft area. And then we built ship after ship after ship after ship, submarine after submarine, through the 60s and in the 70s. Technical requirements were exceptionally conservative. The primary objective was fulfilling the mission on the first try, even though the technology was yet unproven. Let me repeat that. We couldn't do it twice. We couldn't fail. So we had to be exceptionally conservative on how we approached the technical requirements implemented and deployed. It's just a given. And we were fortunate enough, unfortunately, that we could do it, that we achieved this. The Soviet Union did not. Okay, they tried and failed a couple times. And so it put us in a position to regain the lead in this business. We use the Socratic method. Now, does everybody in this room know what that is? I'll explain it to you if you don't. All right? It's basically nothing sacred. Everything can be questioned. You build what you're going to do next based on learning from what you did before. Very heavily a Socratic method, nothing's assumed. And it's a design process that you typically don't find in the commercial world, even today. You don't find it today. Reliance on technically competent personnel rather than management systems. Matthew came up to me and asked me the question why I leaned on process systems. In our earlier discussion, management process systems, okay? It's a reality of the large numbers of people that are involved with the commercial world. You need processes. The naval world's a smaller world, and you specifically depended on technical competence of people solely, and a very ability to manage a much smaller activity. And personal responsibility. Okay, you're accountable for what you do. There is no hiding. You can run, but you can't hide from that particular requirement. This approach continues today in the Naval Nuclear Program. Key messages. Shipyard application of nuclear energy for propulsion is demanding and requires considerably more robust design than a commercial plant. The choice of pressurized water technology for submarine and surface ship application was based on the best available information in a fledgling industry. And we'll talk about that again tomorrow. But you understand, we are doing something here in this building these that there was no industry. There were no standards. The textbooks weren't written, okay? And so you're doing something in that environment and learning and building an industry as you go. And so it's a fledgling industry, okay? You're building it, okay? That's what your job was. And it was driven by the demands of response to Cold War priorities. PWR technology has proven to be the best overall choice for the U.S. Navy, and it continues and has continued over the decades to look at alternatives. It keeps coming back and saying that appears to be the best overall technology for most applications. And the conservative design philosophy has allowed operational challenges to be accommodated and resolved without having a detrimental effect on the mission. That last point is very important. The naval program has not been perfect in what it designed and built and operated, okay? It's had a bunch of problems over the year, which I don't have the freedom to talk about here. But the issue is lots of problems, lots of challenges, material challenges, design challenges. We were able to accommodate them without affecting the mission because of the levels of conservatism of design, something you would not do commercially because it's economically a disaster. Okay? It's very expensive to do business the way the naval program does business, but it was a necessary element and it continues today. It's a military necessity, a strategic posture necessity for the United States. So keep this in the back of your mind as we start talking about commercializing nuclear energy. This is where you're starting, build on that particular leg of the triad, the nuclear triad. Questions on this? Yeah, go ahead. Go ahead. Keep with the mic. We won't all be able to hear you. Oh, if it's not on, turn it on. Tap it. No, it's not on. Turn it on. There's a switch.
Now probably works. Yes.
There, you got it.
All right. So it looks like from what you discussed that you think, at least you're hinting to the fact that if the Navy was not part of the development of the nuclear industry, we may actually end up with a different technology.
I'm sorry, your last part?
Different technology.
Yes.
Okay, so I think that the type of technology depends on the metrics that you are using to measure the performance of the technology. Mm-hmm. So in your opinion, what are the different metrics between the commercial usage of the technologies as the Navy use of the technology? Because safety, reliability, they seems to be the same metrics to me.
Those metrics, but you remember that slide that went through, this is what you've got to do to be a submarine reactor?
Okay.
To be a submarine, if you will, and put a reactor in there. Those are not consistent between this propulsion plant and the commercial reactor. They're different in a considerable number of different ways. In the way, I can't go into the detail in the design of the naval plants, but the issue is one of the way they implemented the designs in their conservative fashion in doing so resulted in a machine that was much too expensive to ever commercialize. You wouldn't commercialize directly off of that machine. It took adaptation of that machine and to bring it into an economic world. There were real questions in the late 50s whether we could ever build an economic commercial reactor, because our experience was being built on these types of machines. Okay? I don't know if I've answered your question or got near it.
Yes, but I think that it would be a good exercise to go through the metrics and see which one they cannot be mapped one to the other and so on. So, measuring the level of diversity of those metrics.
Yeah. Now, let me just note to you, as I'll get into it in this presentation, that wasn't the way the technology evolved into the world. The drive of, besides the fact we're working on this pressurized water reactor technology and setting the stage for light water reactor technology to get complemented by things like borax, et cetera, okay? There wasn't a technology bake-off, if you will. It wasn't we didn't take a bunch of metrics and say which are the best ones. Because the light water reactor technology got driven into the commercial world by policy. not by technology. And I'll go into that right here. Pardon? Okay. By policy.